Greetings, class. This next segment is designed to introduce something that you may have already worked with, depending on how far and thoroughly you got into Chapter 6 in Spatz. But this segment is going to introduce you to another expression of the normal probability distribution, and that expression is known as the z-table, or in Spatz, it's table C, which appears on page 386 and 387. So if you have your book with you, I recommend turning to page 386 and 387 throughout this segment. I have gone ahead and copied and printed, as you can see, and I've also uploaded just this portion from Spatz, to Blackboard, and this is called, this document is named, it's named the actual z-table Spatz. That's the name of the document. Look, if you will, take a look at this particular table. You might see or notice right away that, first of all, it's 2 pages, and I'm going to go ahead and separate mine. It's, let's see, 2 pages, right? They look kind of similar. This is the first page. One of the first things you might notice is that there are sort of 3 broad columns, 1, 2, and 3. And then there are 3 sub-columns within each of those columns, column A, column B, and column C. And then those columns repeat, A, B, C, A, B, C, and then likewise on the second page, A, B, C, A, B, C, A, B, C. It's extremely, extremely important that you know, A, how to calculate z-scores, and hopefully you're good to go on that count, and B, also just as important for the sake of this chapter, extremely important for you to know how to navigate this table. All right? Now, a couple things. One of the things I want you to be aware of is the fact that this table in Spatz, pages 386 and 387, only shows you half of the table. All right? First off, look at column A. Any column A. There's 3 of them on page 386 and 3 of them on page 387. Column A, when you're looking at this table, column A are z-scores. That's what column A is. Column A is or represents z-scores. Okay? Now, you will notice real quickly, if you scan all the way from the upper left-hand portion of column A on page 386 all the way down to the lower right-hand portion of page 387, again column A, you might notice right away that there are no negative z-scores on that table. All right, now, here's a question for you. True or false? Can z-scores be negative? True or false? Well, hopefully you said true, because z-scores can indeed be negative. Negative z-scores simply represent a raw score that fell below the mean. X minus the mean. If x is less than the mean, you're going to have a negative difference, and you're going to likewise have a negative z-score. But back to the table at hand. Z-scores can be negative. However, we only see positive z-scores here. Here's why. You only need 1/2 of the distribution. You know why? Because it's symmetrical. So if you're solving a problem on the right-hand side of the distribution, the positive side, if you will, you automatically should be able to solve a problem on the negative side. So if I had to draw a picture of this table, here's what it would look like, just very quickly. All right, this table would look like. Oh shoot, no, that's wrong. You know why it's wrong? It's because the abscissa touched the curve. Here's what it would look like. This is what that table would look like. It would be exactly half of the normal probability distribution. A z-score of 0 would be right here. A z-score of 4 would be way out there. Okay? Now, if I were to draw the whole distribution as it's represented very roughly with this table, it would look like this. Equals -4, z equals 4, and z equals -4. very quickly it would look like this. It would look like the whole normal probability distribution, bell-shaped curve. There would be a z-score of 0 in the middle, a z-score of -4 way, way out here, and a z-score of +4 way, way up there. Now, we're going to work with the z-table quite a bit. Just suffice it to say, column A in the table in Spatz, table C in Spatz, represents z-scores. Column B represents the area. And remember, area is the same thing as saying probability. Memorize that if you can. Area is saying the same thing as probability. Column B represents the area under the curve between the mean, the middle, and a particular z-score. Okay? So for example, just looking at the table, the numbers, right? I'm going to look in column A. I'm going to look in column A for a z-score of 1.3. Go ahead and pause this video unless you're already good to go on this and look for a z-score of 1.3. All right? Find in column A the value 1.3. That's a z-score of 1.3. And move over one column into column B. What's the value that you see there? It should be 0.4032. What is that number? Well, that means that between the mean, the middle, and a z-score of 1.3, there is 0.4032 between the mean and that z-score. 0.4032, that's the proportion, that's the area of the normal probability distribution that falls between the mean and a z of 1.3. Now don't leave that z-score yet, 1.3, we've only talked about column B. Scroll over one to column C. That also is area, except that's the area beyond a z-score of 1.3, and that area is 0.0968. So if I were to draw a picture of that, I'll draw the whole probability distribution. I just drew a bell-shaped curve. I'm going to put a z-score of 0 right in the middle because a z-score of 0 always goes in the middle. I'm going to put a z-score of 1.3 on the abscissa where it belongs, 0.4032 and 0.0968. That's what this picture would look like using the z-table. The normal probability distribution, a z of 0 in the middle, a z of 1.3, that's just the one I picked out of the air, right? And then I put the area, the appropriate areas where they belong, 0.4032 between the mean and z, between the mean or a z of 0 and a z of 1.3, and then the area beyond a z of 1.3, 0.0968. Also, real quick, what do you think 0.4032 plus 0.0968 equals? It equals 0.5, and it has to equal 0.5 because the area between the middle and a particular z-score plus the area beyond z is always going to equal 0.5. 0.5000. Okay? All right? Let's do another one. All right? Look at the table and find a z-score of 2.01. A z-score of 2.01, positive 2.01. I'm going to do the same thing I did before. A z of 0 in the middle, z of 2.01 on the abscissa. Z-scores are always on the abscissa. Zeros are always on the abscissa. Z of 2.01 has 0.4778, 0.0222. That's how that problem would look. The normal probability distribution, a z of 0 in the middle, and according to the table, a z of 2.1 has 0.4778 in this portion, the area between mean and z, and 0.0222 beyond z. More on this in a little bit.